Okay, so let's start. Um, with this module, we are going to kind of move to a very different uh, type of digital circuits, namely sequential circuits or sequential logic. And in the very first lecture of the course, we had talked about how combinational logic are circuits or systems which provide an instantaneous output corresponding to a function for a given input. So basically, they implement a function which, as the input changes, immediately reflects the corresponding output. So combinational logic literally are like a table. Inputs tell you which row of the table you go, and the output shows that after a tiny bit of delay. But at the same time, we had also talked about that how if we had circuits with memory, that is devices which remember history, they could do more powerful things. We had an example of a calendar kind of system where at every midnight a special signal would come, and we had this block which would remember, which would update itself only at that time. So that was an example of something which had memory, and more generally they are called as sequential logic. So we're going to spend some time now looking at that. So this particular set of slides covers chapter 14. Okay, so sequential circuits are circuits that remember history. Now, unfortunately, history is infinite, like goes back to, can go back arbitrarily into the past, and that's not very useful because that means you have to keep if you want to remember everything about the history of a system, then and all the inputs ever seen, then you will have a growing number of bits to be stored. So a very powerful concept is one of state, and state basically says that that is the information that I really care about remembering. Okay, so I don't have to remember all the inputs seen thus far, but really it's a set of variables that represent all the information that I need for the future. Okay, so we'll see how that kind of works out, and then we'll see that what these digital systems really boil down to is about how do you update the state. So I will take the example of our brain. We have a lot of neurons, but still there are a finite number, and so our memory is finite. And so as we get exposed to new information, we store some sort of a distilled version of that information in our brain, and then of course we forget older stuff. So that process of updating really kind of maps in digital logic terms is that I'll have some element where I can store state, and I would have some strategy of updating that state. And it turns out that there are two very broad categories. That is, we are going to update the state whenever the state changes. That's called asynchronous. And the other approach is called synchronous, where it says, I'm going to update the state, that is, update the memory, only at some special time instance, which are defined by some sort of other signal, like in that example from very first lecture, at every midnight. Or in digital logic, usually there is a clock, and the update happens every time the clock ticks. Our brain actually kind of operates in similar fashion. In deep down in the brain, there is actually an oscillator, a clock, which sends out a signal which is roughly 10 to 20 hertz or so, and our neurons kind of fire in synchrony with that. Okay, so that's how even biology organizes things. So that's the notion of synchrony, and we'll see how sort of that plays out. The basic unit of remembering something in digital logic is an entity called flip-flop, or specifically D flip-flop, data flip-flop. So we'll go over that. And then how you organize these memory elements together with combinational logic to make big systems which store state, update state, create output, which now depend not just on the current input, but also on the past. So a particular form is something called finite state machine. So we're going to look at that, and then how do we design state machines. So that's kind of a whole bunch of things that this set of slides are going to cover. So there are a lot of different things, new things we'll see. So combinational logic, again to remind you, is memoryless. So it literally it basically implements a mathematical function. And at any given point in time, in an ideal combinational logic, what happens is that the output, m bits of output, correspond are a function of some n bits of input, and we choose to represent this function in many different ways, sometimes as Boolean logic equations, sometimes as a truth table, and there are other formalisms that are used by design tools and stuff like that. And as we also discussed, that's the ideal case. As soon, even if one of these input changes, if the corresponding output is, if the output will change, it will change immediately, or after, in real circuits, after a tiny bit of delay. And so that's combinational logic. Sequential logic have memory. And one way of thinking about memory is that anytime we are making a decision, we are creating an output, is not just a function of what we are currently seeing at the input, but also a function of what we saw in the past, of some information corresponding to that. And so sequential logic typically have this kind of structure, that they have this combinational logic, they're creating an output, but this output is a function not only of the currently seen inputs, but also something called state. State is the memory, and so every time, at all the times, what we're doing is the output is being computed as a function of both the state and the currently seen input, and we're also constantly updating the state. So as we see new inputs, new memories are formed, and that goes into the state. So sequential logic will always have this kind of feedback, some sort of a loop in the circuit. Just having a loop doesn't necessarily make it sequential, but a sequential logic will have a loop. Okay, so it's just one-way implication. So the state is a way of capturing relevant information about the past. What is relevant depends upon what you are seeking to do. So like, for example, let's say I want to count number of people entering through a door. So every time someone enters, there's a sensor which sends out some signal, and I have to count this, count the number of people. Now clearly, one strategy could be that every time the sensor sends a waveform, I store that waveform. But that's redundant information, because all I'm seeking to do is count. So the state in that case would be how many people entered thus far. So instead of storing every new input pattern I was seeing, every new waveform produced by that sensor, I would only, I'll maintain a counter, some sort of variable, and every time a new person comes in, I'm going to increment it by 1, and that's my state. So the only relevant thing for this application is number of people who entered thus far. Nothing else kind of matters. So what state you need, it depends on the application, and once you decide what state you need, then you'll also decide how many bits you need to store that state, how many bits you need to represent that state. So for example, again in the people counting example, if I anticipate that over the lifetime of this building, there will never be more than 1 billion people coming in, or something like that, I'll say, okay, 30 bits are sufficient for me to store that. So identifying what is the state and how are you going to update the state. In my example, every time a new person comes in, and how many bits you need, all those kind of decisions one has to make, but that's what goes into the state. So state is relevant information about history. And at all times you are kind of computing, you're also updating the state. As you get fresh input, not only are you sort of modifying the output, but you are also updating the state. Okay, so let's look at an example of a circuit which has state. So let's look at the circuit where what we have is a NOR gate followed by this one. What is this gate? Just this guy, this second part. It's another NOR, right? I mean, it says basically NOR followed by NOR. Okay, but we draw it this particular way. And see, the interesting thing out here is that the output Q is feeding back out here. And then we have these two inputs, S and R. Okay, so it's different from other combinational logics that we have seen thus far, because we have one of the inputs is basically the previous output, right? So at all times, I'm kind of taking this output and feeding it back to the input. And so at every time, I'm calculating the new output, the next output, as a function not just of S and R, but also the preceding value of Q. So generally speaking, you would expect, I mean, mathematically, what we are saying out here in some senses is that Q is some function of S, R, and Q, right? So Q at some t plus 1 depends upon the Q at some time t. Okay, so that's the nature of the circuit out here, that output is updated as a function of the previous value of the output, and this process can lead to all kind of interesting behavior. It can oscillate, it can stabilize at some value depending upon the nature of this function f. So let's see how this particular circuit ends up doing. So if we write the equation for this, so Q is equal to not R and not X, where X is this intermediate value. And then I expand X, so not X is not of S or the old value of Q. And I simplify this thing, I end up with Q is not R or S, and S or Q old. So that's the equation of this circuit. And if we now work out as to what it means, it's basically saying if R is 1, then not R would be 0. So the AND will not matter. So if R is equal to 1, then output is unconditionally 0. If on the other hand, R is 0, then we have to look at the next term. And the next term says S or Q old. So now if R is 0 and S equal to 1, then the new value of Q will be 1. So R equal to 1, Q 0, R equal to 0 and S equal to 1, Q equal to 1. And finally, if the remaining clause, if R equal to 0 and S equal to 0, then Q is equal to Q old. So what this is doing is, if I make R equal to 1, I reset the output back to 0. If I make R equal to 0 but S equal to 1, then I set the output to high. And if both are 0, that is R is 0 and S is 0, then Q remains stable. So this is a circuit which, by controlling S and R appropriately, I can make the output to be 1 or 0, or just have it hold its value. Now this is something we couldn't do with combinational logic thus far, because combinational logic, the output is always a function of the two inputs I'm providing. So there was just no way for us to tell it retain the value. I mean, it would always just compute a value corresponding to whatever S and R we were feeding. So now, hopefully as you can see, that the behavior of the circuit is going to be one where if I make S and R equal to be both 0, then it's just going to keep its value. But I can selectively update it to 1 or 0, as the case may be, by controlling S and R appropriately. As you can imagine, R is called R because it has a resetting behavior. So R for reset, S equal to 1 is setting the circuit. So reset, set, and then if you're doing neither of the two, then it holds its previous value. Okay. So go ahead.
So the reset and set are not intention to be all zeros together.
Pardon?
They shouldn't be all zeros at the same time. R and S.
Well, no. If I want to.
One. Both are ones.
Well, actually, in this case, reset has a priority, right? So if R equal to 1 and S equal to 1, then reset has a priority. I could have designed a different circuit where set would have the priority. So what this is saying is, if R equal to high, reset it. If R equal to low and S equal to high, set it. If otherwise, hold it. Okay? So it's a memory cell to which I can write 1 or write 0 or just have it hold its value. And okay, so with this basic primitive, we can basically, everything else in sequential logic kind of really can be done based upon this basic primitive. You could write a truth table for it, except that the truth table in this case is now a weird table because the output depends on the input. So it's called state table. So for so the same role that truth table was playing for combinational logic is played by state table in case of sequential logic. And the main thing out here is, as you would see, we have the real inputs, S and R,
So these are the inputs. And then we have the old value of Q. So I'm going to, this is the old Q, which means what is currently in the system. In this, so this is kind of what I decided to memorize, right? So this is the state really. So this is the old state. And then the new value of Q, which is kind of the new state, the new thing that I'm seeking to remember, is out here. And what this thing is doing is basically calculating Q, the new Q, as a function of R, S, and Q old. And you can see that if R is high, then independent of what S and the current value of Q is, we make Q to be 0. If on the other hand R is 0 and S is high, then unconditionally Q becomes 1. If R is 0 and S is 0, then the new Q is the same as the old Q. So 0, 0, 0 gives 0 and 0, 0, 1 gives 1. So this is the analog of truth table in case of sequential logic, where not only will you have the inputs, but you'll also have to worry about the state. In this case, the state and the output is the same thing. The Q is also what I'm outputting, and Q is what also my state is. Question?
Is X a constant?
Is X a constant? No, it's just a label I've given to that intermediate wire. Oh, you're talking about the table? Which X are you talking about? In the table or up there?
Up there.
Up on the figure is just a name I have given to that table, to that wire.
How can you get a value for Q if X is not already?
Okay, so I think notational problem at some level. This X out here has nothing to do with the X out here. These X's are the don't cares. Okay, whereas this is just some arbitrary name to the wire. I could have called it Y, and that would have probably been clearer. So it's just a name given to it. It will have the value. The value it will have at any given point in time would be the NOR of S, the current value of Q. Right? I mean, this it has an OR gate, and X at any given point in time is S. S is a NOR of S and Q. And Q in turn is a NOR of X and R. That's the feedback effect. We don't have truth table anymore. We have this state. Okay. Because we have to worry about that there will be something which is both an input and an output combination, right? I mean, so in this case, Q is both appearing on the input side and it's both also appearing on the output side.
So truth table is defined as something the input decides the output.
Exactly. It's a mathematical function. Like when you in your math courses, they define a function to be a mapping from a state, one set to another set, right? Truth table is this.
But why can't we view the QO to be one of the inputs here?
You could. The only thing is that but Q old is the same. Is really physically the same thing as Q, right? I mean, it's the same wire, the same piece of thing, right? So what will happen is that in the circuit, what will happen is when I do something, Q will change, but then in turn that will cause the output of the first NOR gate to change again until the circuit settles, right? So there will be some sort of a rapid flow happening until the time the circuit settles. In some circuits, it may actually oscillate. Okay, I'll give you an example. Let's take the following circuit. Take odd number of inverters and just consider this circuit. Let's call this guy X. Let's call this guy Y. Okay. So now what this is saying is the new value of X is equal to the naught of the naught of the naught of X, which is the same as naught X. So now what will happen is when the circuit powers up, let's say x has some value, 0. The new value of x will be 1, then the next value of x will be 0, and on. So guess what? This thing will oscillate. It will produce a waveform like this in time, where this thing will correspond to so much time it takes to propagate through these inverters. So with feedback, you can have oscillatory behavior in some circuits, and in some cases that's what you want. Or in other cases, like this one, it settles to a value. Okay, that's how the behavior of this circuit. And this is more useful. I mean, this is what more useful circuits will have, unless you're deliberately trying to create an oscillation.
What's the initial condition of Q?
Good point. So answer is it depends. Now usually one way you can say is I really don't know. When it starts up, Q may be a totally unknown state. And so probably what we'll do is, since we start up Q is an unknown state, we want to bring it to a known state. So maybe I'll reset it. I'll make it R equal to 1, S equal to 0, let's say, to reset it, to bring it to a known state. Okay? Another alternative is that you design the circuit such a way that when it powers up, Q is at 0. Okay, and the way it could be done is you create some special circuitry which forces Q down to 0. So both ways could be done. Usually chips and all are provided with a special pin called reset pin. And what you do is when you power up, you apply a little pulse to that reset pin, which just makes sure that every memory element on the chip is brought to a known state. Okay, that's a very common thing to do, but sometimes you may also kind of say, just want to make sure that I have a way to put it into a known state. So like for example, I'm sure many of you have done programming. Let's say in a C or Java program, I write int x. And the program starts. As soon as you enter your main function, what is the value of x?
Could be anything.
Actually, C guarantees that it will be 0. Okay, so the compiler makes sure that those values are initialized to 0. Java does the same.
This sort of settles, but I don't see how, because if Q is not the same as Q, well, possibly since it's stuck here, then it would just stay the same. And if Q is the same as Q, well, then it would just stay the same. Like just the way that this circuit.
Well, this circuit will always settle, right? I mean, so think of it this way.
So it doesn't like change and settle, it just settles on the
Right. So if let's say Q was something arbitrary, and I made R equal to 1, then Q will become 0 immediately, and it will remain there, right? If Q was something arbitrary, and I made R equal to 0 and S equal to 1, Q will be forced to 1, and it will remain there. And if Q was something arbitrary, and I made R equal to 0 and S equal to 0, it will remain at that whatever value it was, right? So there is no oscillation.
Why do we not know the initial state of Q? Because on startup we know the value of S and R. As long as we know the value of S and R.
Not necessarily. R and S could in turn be coming from some other memory sets, right? So we don't know where R and S are coming from. So when you're starting out, you don't know what their values are. So generally speaking, for memories in a chip, you cannot assume they would be in one state or the other. In fact, just to give you some interesting examples, so how many of you know what DRAMs are? Anyone? DRAMs? Have you ever bought memory for your computer? These DIMMs, okay, these little kind of chewing gum size packets you get and you put them into the slot. That's the main memory of your computer. And some studies have recently shown that so let's say you have stored an image or some precious data into that DRAM. Now each cell of a DRAM is nothing but a capacitor which stores a charge. Studies have shown that, so let's say I write something into that DRAM, and what studies have shown is if I power off my computer, I take the DRAM out, I plug that back in, I restart the computer after tens of seconds, the data is still there. So it depends upon what was there previously, okay, because those capacitors retain the charge. So all sort of funky stuff can happen, and these particular people actually made some beneficial use of this property, but you can also imagine this could be used to extract data,
snoop on the memory contents and stuff like that. So going back out there, memory cells, their initial state at a circuit level is, in general, you cannot say anything about it unless the circuit was designed for it. Any further question before we move on? Okay, so this is kind of the simplest of the memory-oriented circuit. Let's see how sort of it would play out with some particular scenario. So let's say we start out with R equal to 0, S equal to 0, and Q had some arbitrary unknown value. It's either 0 or 1, but we don't know what it is. So now let's say at some time t1, R became high. And by our state table, we see if R is high, then Q becomes 0, irrespective of what the current value of Q and the value of S is. So this R going high, after a teeny bit of delay, will cause Q to become 0. So Q now, from T1 plus a tiny bit of delay, after that, Q becomes 0. Then, let's say sometime later, R goes back to 0. And we know that when R goes back to 0, if R and S are both 0, Q retains its value. So nothing happens to Q. Then let's say sometime T2, S became high. Going back to our table, if R is 0 and S is high, so we are in this row, 0, 1, then Q is unconditionally made 1. So we see now that Q goes to high after a teeny delay after T2. And then let's say a little bit later, S goes low. So after this time, S and R are both 0, and therefore Q remains what it was, 1. And then perhaps the process repeats. Let's say at T3, R becomes high. R becomes high. And when R becomes high, then now we are R equal to 1, S equal to 0. Again, bottom row, Q becomes 0. So you see Q going low. And this process kind of goes on and on. Okay, so this is kind of a complete diagram, I think. Okay, so same process kind of repeating here. I'm not going to go through all of them, but by referring back to that state table or state transition table, we can see that how Q is changing, and basically bottom line is that even though we started out with totally unknown value of Q, after that first reset, from that point on, Q has a specific value which we can precisely, if the circuit is working correctly, we know precisely what it is, and you can kind of make, given any arbitrary waveforms for R and S, you can always kind of plot out how Q will be changing. Okay, so this circuit, which we had been drawing thus far, oftentimes you will see drawn this way. They are exactly the same thing. All we have done is we have taken this AND gate with 2 bubbles at the input, we have replaced it by an equivalent NOR gate, and we often draw it this particular way. So you see this kind of a structure, S and R, and kind of mutual feedback happening. Output of this NOR gate feeds into the other one, output of this NOR gate feeds to the other one, and then this output is called Q. So this is called the SR latch or RS latch, and oftentimes you'll see it drawn the way it is on the right hand side. So let's see what kind of places one can use this thing for. So a very sort of contrived example, but I'm sure in aircraft you have seen those call buttons, right? I mean, you want to call the flight attendant, you press the button, you press it, after that it lights up, flight attendant comes, he or she, after taking care of whatever your request was, they press to kind of turn it off. Okay? So what we have is that logic out here. We have a system which has 2 buttons, call and cancel, and there's a light bulb, and what we want to do is, and we start out, everything is off, button is not, neither of the 2 buttons pressed, and the bulb is off, and what we want to do is, we want to call the flight attendant, so you hit the call button momentarily, and the light, bulb should light up, and then later on when we want to cancel it, or we press the cancel button and the light bulb goes off. If the bulb was already off, then pressing the cancel will have no effect. It's already off. And likewise, if the bulb was already on, pressing the call will have no effect. So as you can see, there is a
history behavior out here. That is, what the cancel does is depends upon what the past was. If the bulb was already lit, then cancel means turn it off. If the bulb was already off, cancel means do nothing. And likewise for the call side, if the bulb is off and I press call, the bulb is lit up. If on the other hand bulb was already lit up, I press call, nothing should happen. So starting state, light is off. We press the call button, light turns on. We release the call button, the right light remains on. Next we press the cancel button, light goes off. We release the button and we release the button and light will remain off. Okay. So the way to implement this thing is with our RS latch. You can imagine that the set is connected to the call button and reset or R is connected to the cancel button, and basically we have the implementation of our logic. So pressing call, going back and referring back to our state table, pressing call will make Q equal to 1 and the bulb is going to light up. And then Q will stay 1. Once we release call button, both R and S are 0. And by our state logic, by our state table, Q will retain its state and Q will remain 1. Then pressing cancel means I'm asserting R to be 1 and therefore Q will become 0. Okay. So what happens if call and cancel are pressed together? So call and together mean R and S are both high. So in this particular situation, the preset had the priority, so it will stay off. Now, of course, the reality is a little bit tricky. So let's say you do play the game of like pressing the two simultaneously and releasing the two simultaneously. There is no true simultaneity, right? So when you are releasing it, if you release the cancel even a teeny bit before the call, then it will light up, right? I mean, so there is, all these wires will have slightly different propagation delays and stuff like that. So this hypothetical thought experiment really is very hard to replicate in practice. In fact, if you try it in Logisim will also kind of give priority to one or the other in terms of the delay. It will make one of them happen before the other one. So achieving like two transitions from two signals exactly at the same time is just something that you cannot do in real life or even in a simulation. Okay, so that was the RS latch. And RS latch is great, but it turns out that this type of memory which changes state whenever the input changes. Okay, so like in our particular case, R or S could be changing arbitrarily, or in kind of the more technical jargon, they can change asynchronously. They can change anytime. That causes problems because sometimes what happens is there might be glitches on R and S. We saw hazards many lectures ago. So what might happen is R is supposed to remain 0, but the circuit driving it was designed by someone who didn't take our class, and therefore the circuit had hazard. So there was a tiny glitch, and the memory cell would be reset. Okay, so you don't really want this kind of memory which is very sensitive. Even a tiny glitch on R or S can cause this memory to be unstable. We want more robust circuits. And one way of achieving robustness is we basically say we are going to act upon, we are going to let the memory be updated only at special times, at some special clock tick. And otherwise, outside those clock ticks, R and S can misbehave if they want. If they want to have glitches, that's fine, we are insensitive to them. Okay? So essentially, we want a memory cell which kind of goes to sleep effectively, and then only when a clock tick comes, then it listens and looks at R and S, for example, and updates accordingly. At other times, if R and S are changing, it doesn't want to act to it, and that generally would lead to a more robust design, particularly with all those hazards and all that you've seen before. So such circuits which act only when a special event happens are called synchronous sequential circuits. They are called synchronous because they operate in synchrony with a clock. So there is a special clock signal which provides an event. Usually we think of either a rising edge or a falling edge of a clock to be a special event. And then rest of the circuit, we just decide we are going to update things only when that clock tick happens, or only when a rising edge happens, and otherwise we will not. So that's the notion of synchronous sequential circuits, and let's see how it kind of works out. So again, RS latches are very sensitive. Whenever RNS change, they are going to react to it. They are called asynchronous. It can lead to essentially hard to debug kind of behaviors and often bugs. So most digital design, unless you really know very well what you're doing, most digital design is done in this synchronous fashion, where basically we update the state only when there is a clock tick and not outside that. And usually, like I said, rising edge of a signal is considered to be the clock tick. So there's a clock signal which we send everywhere in our every corner of our hardware, on the chip, whatnot, and then at the rising edge of that tick is when the memory cells will update themselves, not otherwise. In some of the textbooks, they even say, "Thou shalt not design asynchronous circuits." I mean, as simple as that. Now, having said that, there are conditions under which you could design, and they can do some pretty amazing things. And our neighbors at Caltech, they have kind of done a lot of work around that idea. They call, guess what, asynchronous circuits. And the thing is, they could be more power efficient and they could be faster. But designing them is so problematic that for most cases one should stay away from them. Okay, so let's see how it sort of works out. But the basic idea is that, oh, go ahead. What if there are glitches on the rising edge? Then you have a deep problem. So you will have to make sure there are no glitches on. Good question. And the clock part of a hardware is designed very, very carefully. You will so actually another one of those dictates that you will see in textbooks are that thou shalt not use any sort of gates with your clock. That is, clock should only go to clock inputs of your memory, and it should not feed through any like you should not mix it with normal logic gates so that you avoid glitches. So excellent question, and basically clock is a special signal, you design it special. Okay, so what we now have is, what we are looking for now is kind of a special blob. We call it a state, a register, a flip-flop. It has a special input which is indicated by this triangle sign, and our clock signal feeds to it. And the idea is that this is a memory cell which holds its value, except whenever there is a rising edge on this clock line, at that time it will look at its input, and whatever is an input, it will store it. Okay, so it's almost like whenever a light flashes, you will kind of look at something and write it down into a memory thing. From that point on, you're working with that. Next time the light flashes, you're going to do it. So whenever the clock edge comes, it looks this bluish, the cyan color box called state. It looks at its input, and whatever the bits are on the input, if there are n wires and n bits, it stores them. Okay, and if I look at the output of this guy, it is the current content of this guy. Okay, so this memory cell has bits in it. Output is always whatever is the content of that memory cell, but the contents are updated only when the clock edge comes. If I want this thing to be updated on a falling edge, then you will have this triangle and you will also have a little bubble. Okay, so this one is sensitive to rising edge, but if I had this kind of a structure, then this would mean sensitive to not negative edge. Okay, so you can, circuits could be either way. Sometimes they are designed positive clock edge, sometimes they are designed with negative clock edge. But the basic concept again is that the state is a specially designed circuit. It's a whose output is whatever is the content of this memory cell, but the content are updated only when the clock tick comes, and otherwise they remain still. And we don't know. I mean, I haven't told you how to design such a thing, but obviously people have designed it, so that's why we use it. These things go under special names. They are called flip-flops, clock edge-triggered flip-flops. They are sometimes something called registers. But main thing is whenever you see that triangle sign, that's indicating that on that input, it's the edge that matters. Action happens at that edges. And if you don't see that triangle sign and you still see a clock signal, then that means that it's the level of the clock that matters. It's more like a SR latch or RS latch. So this triangle sign, just keep in mind, it's very special. So what's happening in this case is the following. So I have some arbitrary combinational logic. It has a bunch of inputs in, n bits of them. It has a bunch of output bits, m bits of them called out. And then I have another state bits. I have s bits of state. They feed to this special memory cell, the synchronous memory cell. And the output of synchronous memory cell is also s bits. So this is also s. Okay, and so what's happening is that this state register, or it can store s bits. Whenever the clock tick comes, it looks at the s wires out here, and whatever were the contents of those, it stores them out here, and then that's what it's outputting. Until the next clock tick comes, if I were to observe the wires out here, this side, this is called current state. So if I were to look at these wires, the current state is updated every time the clock tick happens. Okay, this thing is called next state. And the real output of my circuit is this out and in. Now, in some cases, some bits of my output may also be part of my next state, in the sense that they may not be mutually exclusive. But those are kind of special cases, like in that I may have the output also being something that I am seeking to remember. We'll see examples of it later on. Okay, so what is happening out here is the following. So this clock signal then usually goes up and down like this. In this particular case, it's the rising edge which is of interest to us. So the time from one rising edge to another rising edge is called the period of the clock. Usually clocks would have equal amount of time spent in low or high stage, but sometimes they could be asymmetric. It could be that more time is spent in high, less in low within a period. Then that ratio is referred to as the duty cycle.
What exactly do you mean by falling and rising edge?
Rising 0 to 1, falling 1 to 0.
How do you know if it's rising edge or falling edge? Is it by that clock arrow?
No, this clock arrow is just showing time. This is just time. Going left to right, time is increasing. Rising edge is this guy. So this is a rising edge. This is a rising edge. This is a rising edge.
So they'll give you that little.
Oh, sorry, I messed up. This is a rising edge. 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 So these are rising edge. Okay, other edges are falling edges. I mean, there's nothing deep about it. I mean, rising is 0 to 1, falling is 1 to 0. Okay, you go first.
But there's X bits of, I mean, there are more than one bit, so which one are we looking at?
Oh, we are talking about clock only.
Clock.
Yeah, so this edge business is only important for inputs where you see this clock signal, this guy. Right? So this is really referring to this. S bits are just ordinary data bits. Nothing, we don't care about their rising. Okay, so the point is that memory cell is going to act when the clock has a rising edge. Okay.
So one rising edge would be one tick.
Huh?
One rising
One rising edge is one tick of the clock.
In
In this case, how do we know that the rising edge is the rising edge and not the falling edge?
If it was a falling edge, you would see a bubble out here. So this kind of thing. You'll see a little bubble before the triangle.
Oh, okay.
Okay. There was a question on that side. No more questions? Oh, okay.
What do you mean current state and next state?
Huh?
Why do you define current state and next state that way?
Okay, so at any given point in time, the output is a function of whatever is on these wires, the in wires, as well as whatever is on these wires, right? And so these wires are basically corresponding to the current, what the system currently thinks is the state. So that's why it's called current state. At the next clock tick, the content of this state will change to whatever is a value out here. And therefore, that is the next state.
So you mean when the clock, when at the rising edge of the clock, then the next state feeds to the current state.
Right.
And they're exactly the same.
For that, just for the duration of that edge, they are the same. Okay.
So you don't change the S to another value.
I don't change whatever.
You just wire them to the input. Wire the S to the input.
No. Firstly, S is number of bits. Right? S is not a value. It's a S. We are basically saying that my state has S bits of information. Okay. Just like my output has M bits of information and in has N bits. So there are S parallel wires out here. Right? This is in logisim terms, is a wire which has S bits in it. And likewise, this input is also a wire which has S bits in it.
The state block, the state block doesn't have anything to the state. It just wires them to the.
No, it internally would be some circuit which remembers. So it would be a circuit which, when the clock tick comes, takes the input and stores it. Okay, it's usually, as you might imagine, it's built using those latches.
So can it at the rising edge it complement the state?
No, it doesn't do any complement or anything like that. At the rising edge, so one way of thinking, let's imagine that inside that state memory, I had a bunch of capacitors. Okay? And whenever the clock tick comes, I connect the input wires to those capacitors, so that capacitor charge up to the right and the charge up to charge, and then I disconnect. That could be one way, for example, you can make that state. There are many other ways. The way I described is how DRAMs do it, but there are other ways of realizing that memory function. Okay. So it's not simply wiring, it has to remember also, right? Because once the clock tick has gone away, after that, the content of the state is what are appearing on the current state wire. Any further question? It's very important to understand the behavior of this blue block. Okay, it's very different from anything that we have seen thus far. So again, think of it like what other analogy can I give? Okay, your brain. Every time you hear a sound, you open your eye. Whatever you see in front of it, that's what you remember. And until the next time, that's what you remember. Okay, so in that case, your opening of the eye is synchronized to kind of some sort of a cue, some sort of clock. But main point being that the memory content is being refreshed only when the clock tick comes. Otherwise, it's stable. And from a circuit perspective, one has to figure out how to make that happen, but and it's done using some complicated configuration of SR latches or using that capacitors type of thing that I was describing to him. Okay, so this thing is the special storage circuit, special memory cell, which is clocked. So now what happens is, now let's see, so let's assume for the moment that we know how to build this special circuit. There are many ways of doing it, but let's say we have a way. Now let's look inside this combinational logic block. So remember, this combinational logic block is producing one group of m bits as an output, and it's also producing as an output s bits of next state, which is what is going back, which is being fed as input to this side, this guy. So if I go inside this combinational logic, I can really think of it as two functions. Remember, combinational logic is nothing but a mathematical function. It's a truth table. A combination logic of this form, which has two sets of input and two sets of outputs going out, I can think of it as made up of two functions. One function we are going to call as the output function, and what this guy is doing is taking as its input the in and the current state and generating out from it. So this output is implementing some function f of in comma current state. And this guy, this other guy, we'll call it the next state function, and we can think of it, it's implementing some function g of in current state. So I can, that bigger combinational logic which has n bits of in, s bits of current state, and which was producing m bits of out and s bits of next state. Again, this is current state, this wire is called current state, and this wire is called next state, and this is s bits. So I can think of this combinational logic internally to have really two subsystems. One subsystem is responsible for computing out, and the other subsystem is responsible for computing next state. And we are just going to call it output logic and next state logic. So this is just a way of drawing it, but it's often useful that instead of thinking about a complicated thing, I'm really going to say that, look, I have two tasks to do. Okay, two functions to calculate. One, which given the input, current values of the input and current values of the current state, current values of the input and the value of the current state produces out, produces the m bits of out. And I have another function, the next state function, which given the same two sets of inputs computes the s bits of next state. And so designing a combinational, designing a sequential logic system really boils down to three things. One is figuring out what your state is. How many bits do you need? And the other two are designing your output logic and your next state logic. Basically, you have to do these three things. Figure out what your state is, how much state do I need, what is that state, and then you have to define these two functions. What is my output logic function and what is my next state function? And all sequential logic, in fact, all digital logic basically is just that. Defining what these two functions are. Howsoever complicated a computer, deep down, that's all they do. Okay, they have a bunch of memory cells, which are the state, and then they have some logic which tells them how to update the state. That's the next state logic, and then they have some other logic which tells them the output lines that are coming out to the rest of the world. Okay, and we already know how to design the combinational logic. We saw Karnaugh maps and stuff like that, so we already know how to design those two things. And so really as an engineer at this stage, you have to do these design. The problem which comes is that these things would be enormously complicated. So if you think about like how many memory cells a CPU chip has, even if you take a low-end processor, some 8-bit microcontroller which you find in your toaster oven, something like that, that alone probably will have a few thousand bits of state, if not more. So, and then it probably has a few tens of lines coming out as output, as input, controlling various kind of things in the toaster. So even a low-end system could be pretty complicated as things go. By the time you hit big computers and all, your state bits could be perhaps billions of bits. And so you're dealing with very complicated logic. So as engineers, then much of the time we spend doing is to simplify things. We take something complicated, chop it up into simpler subsystems, and we design the simpler subsystems and we wire them together. So what basically has happened is around this core theme that all sequential logic can be viewed this way. Rest of it is really about, can we come up with ways of designing different types of combination logic which are easier for us to engineer, okay? Which may apply to some kind of applications very well, some may be good for arithmetic, some may be good for some other things, but deep down, everything basically, this is the essence of everything, right? The notion of state, that I have some sort of a module which is a memory cell which updates only when a clock tick comes, and then I have these two pieces of combinational logic, one which given the current state and given the input gives me the output, and the other which given the current state and given the input calculates the next state which will go into that cell when the next clock tick comes. Any questions on this?
So is it different, this model and the flip-flop logic? Are they different? We have a class here.
This is the flip-flop. A state is a bunch of flip-flop, one flip-flop per bit. Okay, but we have not seen flip-flop yet, so we cannot talk about them. But basically, one common way of representing or implementing the state is that you basically put a flip-flop with this clock bit tied to the clock and one clock bit.
Sorry, what I meant was RS.
No, not RS. RS Latch did not have a clock input. So we need to do something special out there. So we have not gone into how to implement the flip-flop. Any other questions? So let me ask, if no one wants to ask questions, so let me ask you guys a question. So let's imagine, I make a change on one of the input lines. So I have n bits of input. Let's say I cause a change in one of the input lines. Do you think out can change immediately? Yeah, because it's just going through a combination. What about next state? Can next state change immediately? What about current state? Can that change immediately? No, right? And that's the key distinction. Current state can only change when the next clock tick comes. Until then, I'm free to change input, and it will not have any effect on the current state. Okay? But both out and next state can keep changing. Let's say I want to design sequential systems where changing the input will not affect the output immediately. So let's say I'm interested in those systems where output will not change immediately if the input were to be fiddled with. What would that mean in terms of my wiring? What should I not do? Do not feed what to? Do not feed input to output. Another way of saying is that my output logic should depend only on the current state. Right? I mean, if I were to make a system where this little red line were to be not present, that is output logic used as its input only the current state, then changing in will not matter. It will not affect the output. And that category of sequential systems are very special because they are nice. Output changes only at whenever current state changes, namely therefore it changes only on clock tics. Whereas the way I have drawn currently, when everything connected to everything, if something changes on the input, if there's a glitch on the input, potentially one of the output wires can also change its value. The glitches propagate, which can be bad for us. So that concept leads to two subcategories of these sequential systems. One is called melee, which is what I had previously shown. That is, output can depend on both input and the current state, and next state obviously can depend upon both. Next state can depend upon current state and input. There's a subcase called more machines, and there you see how this output logic at the bottom, it does not depend upon the input to the sequential system. It depends only on the current state. Okay, so that's called the more machine. Melee machine, more machine. Moore machine has a property that output of the whole system changes only when current state changes, which is equivalent to saying output changes only upon clock ticks. Whereas in a Mealy machine, outputs can change arbitrary amount of time. Now, if I were to say that, hey, I have a system where next state does not depend upon current state, what kind of system would that be? Anyone? Like, if I were to say, let's imagine this little black thing going here, current state is not feeding to next state. What does that mean about my system? Huh? So, do you think it's not sequential? It has only one clock tick of memory, right? I mean, so you can still, because what may happen is so this is what I'm saying. Let's say this thing disappears. So that means my output depends upon the current input and the current state, but which in turn can depend upon what was fed a clock cycle back. So it has only, it can only depend upon current input and the input seen in the previous cycle. Okay, it's not obvious to you, so let's draw this thing out. Okay. So I have just drawn it this particular way. So this is our state. This is our next state logic. This is our output logic. And what you see out here is next state logic is not depending upon the current state. So this is the current state. And this is the next state. Okay, so if you stare at this thing, you see that this output is the output by this output logic. It depends on the current input immediately. And then it depends upon whatever is the current state, but the current state is just what is a function of input one clock cycle ago. So this particular circuit is sequential. It has memory, but it has memory only up to one clock cycle ago. No more, right? Because every time what will happen is my state out here will be updated based upon what. So this here we just has some function of f of n, right? Because next state logic depends only on input. So I have some f of n. So what this guy is doing is it's remembering f of n as it was a clock tick ago. Right? Because every clock tick, this guy will remember f of n. And therefore, my output is nothing but out is some function g, which corresponds to this guy, of n and n at the previous clock. So this is a special case where I have only one clock cycle of history. Whereas the more general case, I may remember something from way in the past. Okay, so amount of history that can be in the system can kind of depend also. So you'll see some examples of both, but this kind of thing often occurs also where I may just want to say, always give me the output of current input and the previous input. Then this is what it will do, right? I mean, let's say you are getting a bunch of measurements from a sensor.
And what your task is to design a system where every time a new sample arrives from the sensor, gives the value of, gives the sum of current measurement and the previous measurement. Then all you need to do is to measure, remember the previous measurement. Right? Whereas on the other hand, I may ask you something like, whenever a new sample arrives, give me the sum of all the measurements received thus far. Okay, in which case your history has to remember the sum, which really is dependent upon the entire. There's a question.
What does it say on the writing over there?
OL is output logic, OUT is output, NL is next logic, next state logic.
Oh, the bottom part. Like the
OUT.
OUT.
Yeah, sorry. OUT equal to G. This is the G. And this is the F. Okay, this is next state logic. This is output logic.
Just using shorthand. Okay.
But our basic kind of our general combinational logic system is this. It has the full connectivity, but then all these special cases where something is missing or the other. Most important one to remember is this Moore machine or Moore systems where the output depends only on the current state and it does not depend upon the inputs directly. These have the desirable property that outputs change only when the clock tick happens. So Mealy versus Moore, what are the trade-offs?
So one
So the one you drew just now was me, right?
which one?
The one you drew just now was me.
Oh, this one? Okay, so you tell me, is it Mealy? Yep, because output depends upon the input.
So how many of you have heard the term pipelining, parallelism, pipelining? Is there a question or you have heard? You have heard. Okay, so what does pipelining mean?
Well, you have sequential logic, and you have a bunch of sequential logic devices or something lined up together, right? Instead of saying propagating like one piece of data through them at a time, you just propagate them like one data each. It's pretty much an assembly line.
Yeah, exactly. It's an assembly line. How many of you know the concept of assembly line? Who invented it? Who invented assembly line? Ford, right? So what was the main innovation? Instead of just handling one car all the way through, you have stations, and each station does some work, passes it on. So at any given point in time, you have a bunch of cars at different stages of completion in our system. Okay. So what's happening is you can think of it as those stations are like combinational logic, and then at a clock tick, they hand over their finished product to the next one. Okay, and in fact, assembly lines, they usually do run on a clock tick because they have to kind of make progress the same way. So pipeline logic is basically combinational logic, state, another combinational logic, another state. They are just kind of chained up like this. And what's happening is that my eventual data, which is computing something complicated, but I have multiple partially done things along the way. Okay, so that's another very common example of sequential logic that is encountered because pipelining, or assembly line, what is the advantage?
You don't need to know everything.
Huh?
So what's the advantage of an assembly line?
Uh-huh.
One person doesn't need to know everything. They just need to know one specific.
Okay, but let's imagine I had n teams where n specialists. Okay, so I could have in the model non-pipeline. Start with the raw material. Specialist 1 does this task, hands it over to specialist 2. He does this task, and so on and so forth. When the car is produced, we start on the next car. What's the problem with this one?
If one of the specialists takes longer to work than the other ones, then this and that's going to get like problems or places. So you need to control like when that gets better.
Not quite. I mean, okay.
there's an error starting with specialist 1, so when it gets to specialist 3, he might not know about it?
Well, no, not really. I mean, the answer is much simpler, right? I mean, specialist 1 did its task. While he's doing the task, he or she is doing the task, other specialists are sitting idle. Then the specialist 2 is doing the task, others are sitting idle. The specialist 3 does its task, others are sitting idle, right? And that's not good. So so the assembly line notion basically was not only do we have n specialists, but they are all kept busy, okay? And we arrange things so that each one of takes roughly the same amount of time, so that when specialist 1 is finishing the task corresponding to that station, specialist 2 is finishing the task in that station, and then each one of them does a handover to the next one at the same time. Okay, roughly speaking. Same concept in digital computation, that if I have to do some complicated computation, instead of doing it in one go, I make it break it down into apply function 1 on the data, take its result, apply function 2 on the data, and so each one of these functions is nothing but a combination logic, and then I put the storage entities in the middle, in between these stages, so that at the clock tick, everyone hands things over to the next one. So that's pipeline logic or assembly line digital logic, if you were to call it that way, and that's just another special case of sequential logic. So you'll find sequential, all digital computation, any non-trivial digital computation is sequential, and that basic diagram that we have been using is sufficient to express everything. Some of you may have heard of things like Turing machines and all. You cannot realize those because they have infinite memory. Anything real, anything physically implemented is basically a sequential logic like this. The only thing is you may structure it in many complicated kind of looking ways, but fundamentally that's all they do. They have memory, which is updated in most implementation of the clock tick. You have something which computes the output, and you have something which computes the next state. And that's all there is to all sequential logic. So, what?
So what's the trade-off between?
Yeah. Okay. So good. Sorry, I just said. So one trade-off obviously was a positive I had defined, which is for more machines, the output changes only when the current state changes, which only changes when the clock tick happens. So therefore, in more machines, the output changes only when the clock tick happens. So any glitches which may come in between clocks are not propagated forward. So it is better behaved. Okay, so that's one. Can any of you think of some advantage, disadvantage? Huh? Melee is fast. Yeah, excellent. Why? Immediately, right? I don't have to wait until the next clock tick. Did everyone get that part right? I mean, in case of melee, the input can immediately affect the output, whereas in case of more, any change in input has to wait until the next clock tick before the output will see. Okay, so more is slow as a consequence, and so the thing is, if your clock is sufficiently fast, and nowadays our clocks and computers run at what speed? Anyone? I'm sure you all have laptops and PCs and all. So what's the fastest? What kind of what gigahertz, megahertz do you see? Huh? How many gigahertz? How many gigahertz do you see? Usually nowadays 3, 3.5, 3.8, something of that order. Okay. So it's pretty darn fast. So the point being that whether it's melee or more, for all practical purposes, that delay is tolerable. Okay. But when computers clocks used to be slow, or even now when you are looking at very low-end kind of systems and all, that latency can matter, and in which case you may decide to go for melee, but then you have to do it very, very carefully. Okay, so sort of that disadvantage of more is pretty much the other thing I had in mind. The other things are kind of like melee versus more. It's possible that one may be cheaper to implement, that is, need fewer gates than others, but those are less clear. But again, generally speaking, you would see that people stick with more machines because of this whole issue of glitches and stuff like that. It's just a safer design.
Okay, so okay, so what? Okay.
So why do you mention the pipeline? What's the relationship to median?
I was just mentioning that how even things that you don't think of as median mode, they are just special cases.
So the pipeline is median.
You can anyone? Pipeline machine. So let's look at a pipeline machine. So let me insert a page. Okay, so let's say I have this system. Some input coming in goes to combination logic 1, state 1. Combinational logic 2, okay, so this is a pipeline system. Is it medium mode? It's more, right? Output does not depend upon the input. Okay. Now, is it obvious to anyone that why it is equivalent to the way I was drawing the combination sequential logic thus far? Can you kind of put it into the same form? So what I mean by that is, can I draw it this way? So I guess the assertion I'm making is that I can redraw this circuit so that it looks like this. So anyone, again, this one can be redrawn to look like this, which is what I said, all sequential circuits look like this, right? That's the assertion I made, and I'm saying that this is just a special case of that. So I'll include it as a homework problem. So I'll think about it. Okay, so, but again, kind of the main point I'm basically trying to make is that all digital systems are sequential systems, all digital systems of any physical nature, and they all basically are variants of this guy. So that's kind of the main message that I want to give. Another way of saying is, if you know how to design these things well, you can design anything. Okay. So now the one part we haven't covered is what is that magical state block, right? I mean, I kind of said, okay, it only updates at the clock gate. We haven't seen any circuits thus far which have that kind of property. Like that. We don't know how to implement those. So let's talk about that. So it's represented a single bit. If I want to store one bit of state, then it's something called a D flip-flop. And therefore, if I need to store S bits of state, all I do is I use S of these. This D flip-flop has a 1-bit input D, has a 1-bit output Q, has a clock, which is denoted by this triangle sign, and since there is no bubble out here, so what it means is it's a D flip-flop which operates on a rising edge of the clock. So Q outputs a steady value normally. Whenever clock has an edge, then Q changes to the value of D at that clock edge. And then the clock edge goes away, and now Q has the value which was at the previous edge. So this flip-flop stores 1 bit of state, and by ganging up multiple of these, by having n of these with their clocks all tied together, I will have n bits, a D flip-flop which has n bits in it, okay, which can therefore store n bits of state. Sometimes, like in LogicSim, you will find that this D flip-flop has some additional inputs. It may have inputs called enable. So it might have an additional input called enable, which basically says that this update on the clock edge happens only if enable is high. So LogicSim, I would like you to go into LogicSim and kind of see its D flip-flop. You would see it has an enable signal, which basically says clock is enabled. If enable is low, clock has no effect. Sometimes you will also see signals called asynchronous set and reset. So there might be a set and a reset signal, and they have the property that if I have an asynchronous set, then when I make that input high, then Q will become 1 independent of what the clock is. And likewise, if I have an asynchronous reset, then if I make that high, then Q will become 0 immediately without waiting for the next clock. And these are usually designed, put in for if you want to do a little bit of asynchrony into your thing, very carefully done. And likewise, some of the times they have synchronous set and reset, which basically do the same thing. A synchronous set is an input, which if it is high, will set the Q at the next clock tick. And likewise for reset, reset would be a special signal, which if it is made high, then Q will become 0 at the next clock tick, independent of what D has. So, but the most simple D flip-flop basically just looks like this. Everything else is kind of sugar coating around it. At the clock edge, Q gets the value of D. All the other times, whatever was the value of D at the last clock tick is put in out here. Okay. Now, oftentimes you have to store multiple bits. So what you will do is you will take many of these D flip-flops. You will tie together their clock signals, as you see out here. So a single clock feeding to all of them. But the different D flip-flops work on different bits of my information. So now what we have, this is often drawn as shown on the right, where you see that input D has S bits and output Q has S bits. This is a S bit D flip-flop. Sometimes, or more commonly, it is called an S bit register. Okay, so bunch of bits together is called a register. In CPUs, if any of you have done CS33, for example, I'm sure you would have seen like CPUs have registers and they do operations on them. Those registers are nothing but these sort of D flip-flops. Okay, they store S bits of it. Let's say okay, so D flip-flop, registers, clocks, they are all available in LogicSim. So if you go into kind of the library out there for in the modules, you would see that it has all. They have a flip-flop thing. You can kind of use it very much like that.
Can you explain the edge on clock? I'm not really sure.
Can I explain which part?
The edge on clock changes to
Edge on clock changes Q to D. So at the edge, the flip-flop updates its state.
What's the edge?
No, edge is the 0 to 1, right? Rising edge. Right? When the clock signal, at the time the clock signal changes from 0 to 1, right at that moment, whatever is on D gets stored.
You're saying how when it's high, asynchronous.
Ignore that part. I mean, right now it's only in the second bullet, right? So all it is doing is that flip-flop has memory. That memory is updated with the value on D only when as the clock edge is going from 0 to 1. At other times, changing D has no effect on content. Okay, and it's doing it only on the rising edge because our clock does not have that bubble in front of it. Okay, so that's the second bullet. A rising edge on the clock changes Q to be D because at the rising edge, the flip-flop's memory is updated, and output Q is always reflecting whatever is in the flip-flop, whatever is in the memory. Okay. So this is exactly the same thing as that cyan color box we had in earlier example. Okay. doing exactly the same. Now, this additional stuff, what we are saying is the following: enable. So sometimes you would see that there is an additional signal called enable. And this says that if enable equal to 0, then a rising edge on clock has no effect. So literally, enable is saying enable the flip-flop. Okay, if enable is 0, then flip-flop just retains its old value irrespective of the clock.
Why would you want?
Huh?
Why would you ever want to use?
Because there might be times I don't want the clock, the content of my register to change. Like for example, sometimes it is done to save power. Okay. But there are lots of other values. Okay, so that's the enable concept. Asynchronous set and reset. So let's call them AS and AR. So AS equal to 1. If AS equal to 1, then make Q or the content of the flip-flop to be 1. So immediately, without waiting for any clock signal, as soon as AS is made equal to 1, the flip-flop content changes to 1. And likewise, if AR equal to 1, then Q becomes 0 immediately. And the utility of this is usually at power up. When power up, contents of the flip-flops are unknown. So what we do is you usually blast out a reset signal to all the flip-flops so that they go to a 0 state, or blast out a set signal depending upon. So asynchronous set and reset are useful to kind of just, irrespective of the clock, just bring things to a non-state. Synchronous set and reset, SNR, same behavior, but on clock edge. So what I mean by that is, if S equal to 1, then at the next clock tick, Q will become 1 irrespective of whatever is on D. So it is a higher priority input than D. And likewise, if R is high, then on the next clock tick, next rising clock tick, irrespective of whatever is on D, Q will become 0. So it's just a schedule. Let's see if you can implement this thing. So let's say I give you a D flip-flop. Okay, and now I'm asking you to design a system which does the following. It has two inputs, D and S. It has a clock and it has an out. And what I want is the following. If clock has an edge and S equal to 0, then out equal to D. Else, if clock has an edge and S equal to 1, then out equal to 1. Else, that means there is no clock edge, then out retains value. So let's say I want to implement this, right? And all I have given to you is the D flip-flop and whatever gates you can use, gates or building modules, right? So one way I could approach this thing is the following. I could say something like the following. So I can feed this clock out here. So this is my regular D flip-flop. and that will do the trick, right? Because if S is high, then the output of this OR gate would be high, and the flip-flop would be set to 1. If on the other hand S is 0, then D has an effect. So all these things, synchronous set reset, asynchronous set reset, these are nothing but additional gates which are surrounding the simplest D flip-flop to provide some other commonly used functionalities. But if you understand this basic one, then all the others you can implement depending upon the circumstances. Let's try something else. Let's say, yeah.
Can I have another look at the graph?
Another look at what? The flip-flop? Oh, sure. Which one? This one? Yeah. Okay. So let's imagine I want to create something different. I want you to create a module which takes a clock input, which has two data inputs, D1, or let's call them D0 and D1. It has an output called Q, and it has an input called select. And what I want you to do is the following. If clock has an edge and select equal to 0, then Q equal to D0. Else, if clock has an edge and select equal to 1, then Q equal to D1. Else, Q is stable. Right? So now I want to create a D flip-flop which takes two data inputs, and then depending upon this control input select, I want to load one or the other. Okay? It's kind of like saying in programs you may have a variable x, and I want to say if some condition, then x is equal to 2. If some other condition, x is equal to 3. X is my variable. So how, can anyone suggest a way of implementing something like this using the D flip-flop that we have previously seen and any combinational logic that you want to use? Huh? Okay, it's a multiplexer. Okay, so anyone with multiplexer and a D flip-flop, can you implement that? D is the output of mux, and what are the inputs to mux? So let's try that. So I'm going to use a D flip-flop. I'm going to put a mux. Okay, now what? What should I do? Select goes to control bit, and D0 and D1 goes out here. Okay, so what's happening out here is that at the clock tick, is the output of this mux that I'm going to put into the flip-flop, and the output of that mux is D0 or D1 depending upon what setting. So muxes together with flip-flops can let you now have this sort of conditional storage capability. That is, I'm storing something, storing one or the other depending upon what the value of select is. So you'll find, generally speaking, it's a very powerful combination to have registers with muxes and some simple logic before it to be able to implement all sort of more complex behaviors.
Can we also try to use that source?
You can use anything you want. Okay, let's say I want to create, I have given a clock to you. The clock is some sort of a square wave, right? With, and I want my output to change. every clock tick. So like what I mean by that is every rising clock, every rising clock tick. So what I mean by that is if let's say on clock edge number 1, the output changes from 0 to 1. On clock edge number 2, I want the output to go from 1 back to 0. So I wanted to toggle every clock edge. How would you do that? I want to hear from that side of the class. One, okay. Input of what? D is not Q, right? So let's. So what's happening is that at every clock edge, I'm going to latch onto the, I'm going to put into the memory cell whatever was previously there. So I'm basically toggling the contents of the flip-flop at every clock edge. So if my clock is this, then my output, let's say output started out 0, it will look like this. What is it doing? So what's the relationship between output and clock? Huh? Frequency divider. Yeah. If my clock is 1 gigahertz, output is 500 gigahertz, right? Output looks like the clock, just with twice the period. So frequency divider is a very useful thing to have. We can oftentimes we need slower clocks, faster clocks, whatnot. So that's it. So again, I guess the main thing I wanted you to kind of take away from here is that by creatively combining D flip-flop with simple combinational logic, you can create kind of interesting kind of behaviors. So we saw this kind of muxing thing, where I could load one or the other. We saw this frequency division kind of stuff and other things like that. So very common type of question that you'll see in homework and exams and all are where we'll give you some simple behavior and expect you to design using flip-flops. And now there are systematic ways of doing it, right? Which we'll see. Right now we are doing it on an intuitive basis. The flip side is also very important. Given some assemblage of flip-flop and combinational logic, being able to reason what is it that it's doing, okay, what's the behavior of it. I think that's equally important. So, we'll see how it sort of goes on. Okay, so now let's see how in general these things are going to play out. A general sequential logic. Oh, go ahead. Yeah, we have not talked about it. And we'll actually never talk about it. In the sense, I'll give you some indication, and the point is, designing good D flip-flops requires circuit knowledge, which we don't have. Okay? But trust me, they exist. Okay. So now let's look at sequential logic, which I'm just going to redrawn. So I have, again, our combinational logic out here. I have this D flip-flop, which is storing a state register. So output of this combinational logic is out, as well as next state. Next state is fed as input to the D flip-flop. Output of the D flip-flop is our current state, which feeds back into the combinational logic, and the other input of the combinational logic is out here. So now let's see how kind of this thing will play out over time if I were to kind of look at a specific system scenario. So let's say when I start out, in is A is some value, some n-bit value. So in is A. The output here of this combinational logic would be, let's call it SB, and which is f of A comma SA, because it would be some function of A, which is the value out here, and SA, which is the value out here, which is the when we started out, our flip-flops will have some state in them, some memory, some content in that memory, and let's say that content was SA. So what's happening is at beginning, I have A out here, I have SA out here, and therefore this next state would be the function of A and SA, and let's call that guy SB. And output will have some other value which is a function of A and SA, but we are ignoring it for the moment. We just want to see what happens in state. So this is how we are starting out with, right? At the beginning, the flip-flops had these S bits of flip-flop had the value SA in them. So the wires out here, these current state wires, have the value SA on them. And my input is A, and therefore my next state is a function of A and SA, and let's call that SB. Now, after some time, a clock tick will come. And what will happen at that clock tick? So let's say, so you started out this way, after some time there is a clock tick, a clock edge comes. Positive rising clock edge comes. What do you think will happen now? SA will become SB, right? So what will happen is, at this clock edge, SA, this state, instead of SA, now it will be SB. Okay? Now, this SB is stored out here and in this register and is also visible out here. Okay? My input is still A. Okay? And so now what will happen is, after some delay through this combinational logic, since this in is stable, nothing has changed out here, but this thing has changed, so its effect will start floating through. But meanwhile, let's say also after some time, input is also changed, so input becomes B out here. So what will happen is the net effect of this is that after some time, so this new input, this SB and this new input B, all of that will combine together, and I will get a new value for the next state out here. Okay, so so at the clock tick, SA changed to SB, and around that time or a bit later, input also changes in our particular case. Before the next clock tick comes, input changes from A to B. So what will happen is after some time, we will see that this guy will have some value SC, which is now a function of B and SB. And at the next clock tick, same process will repeat. Did my animation screw up? I think so. Okay, so what you would see is that at some stage, this state will change to SC, and I think that's where I have a typo. Okay, so at a clock edge comes, and at that clock edge, now SC gets locked, and therefore I will see an SC appear out here. And then the same game will repeat, that after some delay, I will see a new value occur on the next state. It would be SD. And then at the succeeding clock edge, that SD will latch in, and so on and so forth. So after some time, I will see an SD occur out here. SD is going to be a function of the input at that time C and SC. And again, at the next clock edge, that will get latched into the register. So next clock tick, again, at this clock tick, this SD will get latched. And then right after the clock edge, I would see that this guy will move from SC to SD. And that whole process repeats. So every time a clock tick comes, whatever is at the input of the flip-flop gets stored. That affects the state wires. And after some delay through the combinational logic, by the time the next clock tick comes, I would have a new value of the next state. And that will get updated. So every clock tick, I'm updating the state. And the input to the flip-flops are being refreshed because the state is changing. So every clock tick, state changes. So the stop wire changes. And meanwhile, my inputs may also be changing as an example. and they together combine so that by the time our next clock tick comes, I have a new value of the next state ready, which again at the clock tick I'm going to latch, and the process kind of keeps repeating again and again this way. So, so at no time, these flip-flops are really playing a very important role. At the clock tick, just really for infinitesimal time, all they're doing is they're just looking at the input, storing the value, and then they become insensitive. They are insensitive to the inputs at all other times. So after the clock tick, if this guy changes the next state, no effect until the next clock tick. So what that means is that my combinational logic has until the next clock tick to get the new value of the next state ready. Okay. So if I'm running my clock at, let's say, 100 megahertz, then that means after a clock tick, the next clock tick will come 10 nanoseconds later, and I have therefore 10 nanoseconds to get ready. So my combinational logic needs to be fast enough to prepare the next value for the next value for the next state in 10 nanoseconds, so that by the time the next clock edge comes, I have the value ready. And this process kind of just goes on ad infinitum. Okay. Before I move on, I wanted to also try out something. Let's look at okay, so let's say I have a clock and I have a D signal like this. And I want you to tell me how the output would look like. So let's say this is a Q, and to begin with, let's say Q is 0. So can anyone tell me when will Q change first? So what will happen at the first clock edge? It becomes 1. Okay. So at the first clock edge, it becomes 1. Now what happens? When will Q change next? All the way goes down to the end. Okay, so now let's see what is happening now. Next possible time Q can change is at the next clock edge. Okay, because flip-flop changes its content only at clock edges. So let's go to the next clock edge. Until the next clock edge, we know it remains 1. At this clock edge, D is again 1. So nothing happens. We continue. Now we go until the next clock edge. Again, D is 1. Remains that way. And next clock edge, D is 1, remains that way, and remains that way. So see, this D going to 0 for a short period of time had no effect, because the flip-flop is looking at the D only at the clock edge. Okay, so these for effect of any change in D to make it true, it has to be visible at the clock edge. Okay, so in these things, again, bear in mind that Q will change, Q can potentially change only at a clock tick, at no time else. It may, depending upon the value of D, it may remain stable, but it certainly cannot change at any other time. So, very important for you to kind of get comfortable with this thing. I think we are out of time, but the TAs will go through additional examples and all of this thing.